Alright, hey guys, what's going on? So we are now going to continue with Chern-Simons theory. I apologize also for being somewhat sparse on YouTube. I've been working on my animations, been working on my website, and that's sort of consumed my time for a little bit, but I'm going to try to come back and also give you these style of lessons as well because they're easier and faster for me to develop and to get out to you guys. So again, my apologies on that front. Make sure to hit that like and subscribe button if you want to support the channel. And if you can also go onto my Patreon page or become a member here on YouTube. Now that all of that is out of the way, let's go ahead and get started with Chern-Simons theory. Or continuing with Chern-Simons theory. So we've talked about a lot, right? We've talked about a lot of topology. We've talked about now sort of casting electromagnetism within the context of differential forms. So now we're going to get to the quantum Hall effect. And what I'm going to do here is I'm going to actually follow Dr. David Tong's lectures on this. And because I quite like those lectures, right? But he doesn't go into great mathematical detail in some of his stuff. So the difference between the lessons I'm providing here and his lessons is that I'm just going to try to go into more detail, go through more derivations so that things are a little bit more clear and you're looking at equations from sort of a more, I don't know what to call it, from an approach that's more axiomatic, I guess. You don't have to go back and forth between websites to see where he gets some of his equations. That's what I'm trying to get at. Anyways, so we're now going to turn to this important sort of milestone in experimental physics, right? So when humanity saw the double slit experiment, that was a big deal, right? That gave us the understanding of wave-particle duality for fundamental particles, particularly electrons. The quantum Hall effect is kind of similar to that. It's not something that everyone knows about, like the double slit experiment, but it's sort of, if you're a critical thinker and you're very much into physics, then the quantum Hall effect is going to be the next sort of big thing that is going to open your eyes, hopefully, to the weird and strange world of modern physics. Okay, so we are going to turn to this now and make sense of it using Chern-Simons theory. Okay, so imagine you have an electron. It's traveling and it's confined to 2 dimensions. Okay, and you do this through very thin graphene sheets. Okay, I think that scientists did it with other types of materials, but when going through this paper, graphene, I believe, was mentioned. This was named after Edwin Hall in 1879, this effect. And basically the effect is going to tell us that there's going to be this weird resistance that is sort of quantized when we apply an external magnetic field to a particle traveling or in a confined 2-dimensional plane. Okay? Let's see how this works. So recall from basic electromagnetism, right? I'm gonna assume that you kind of know a little bit about electromagnetism. This is, I believe, one of Lorentz laws. The change in the velocity of our particle, okay, is proportional to the cross product between its velocity and the applied magnetic field. Okay. So if our particle is traveling in only 2 dimensions, right, we only have x and y coordinates. So the velocity is the velocity in the x direction, the velocity in the y direction, encapsulated in some vector. Okay, and then we're going to apply a perpendicular magnetic field. The perpendicular magnetic field is given by this, right? It's perpendicular. It's in the z direction, right? It's pointing up here, so we can imagine we have I'll undo that. We can imagine we have coordinate system. This will be in x, this will be in y, and this will be in z. Z, I say z and z. I interchange how I say it. I'm not English, actually. I'm American from the West Coast, but that's nor here nor there. This so here's our setup, right? Our setup is the velocity of our particle is proportional to the applied magnetic field. Okay, so we have two coupled equations of motion now, right? Because we have this is a vector, right? And so we can take the time derivative of this, right? And so we get this when we do the cross product between this and this, and then we get this one as well. Okay, and so now, okay, so let's propose two following solutions and check them. Okay, or a solution, right? Because this is actually a coupled differential equation, right? We have x here and x here, but then we also have y here and y here. So we're going to say x, so the double derivative actually of x is this guy. The double derivative of y is right here, right? So this is right here. This guy is right here. This guy is right here, and this guy is right here. Okay? Putting this all together then, we say, well, okay, so let's deal with this one, right? So this guy here is going to be, so this times m, that's this right here, okay, is equal to this E times B times this guy right here, which is this, okay? And so we have, so let's see, E times B, here we have R, and so we have, and then we have, so here's our E times B, R, EB over M, and then this guy here we said was this one right here. We have this R, this should not be squared, right, because that's just R. And so we have this M times all of this, which is right here. You can see, right, so R, and then we have E squared. There should be an E squared in here. That's probably why it has a squared in there. There should be an E squared in here. Right, so we have R E squared B, R E B squared, R E squared B squared, R E squared, because we have this E multiplying up here, B squared, B squared. Right, so you could see that this actually checks out, right? So if we have, so these guys are the equations that tell us the position of the x and the y position of our particle traveling in our two-dimensional plane under the influence of an external magnetic field. Okay? So here's our external magnetic field again. It's in the argument of these trig functions. So we can see that this all checks out, which tells us that we have discovered the correct solutions to the coupled differential equations. And we could see, the effect of an electric field, E, would be on this motion of the particle. Well, that's the next question we want to ask. The key thing here, okay, so we have the idea that, okay, an external magnetic field is going to cause this oscillatory behavior in the positions of our particle. Okay, and that's all fine and good. We have an external magnetic field, generates this oscillatory behavior in the positions. What about an external electric field? Okay. Well, the one thing we want to keep in mind here is that if we play our cards right, then we should be able to recover Ohm's law in the presence of a magnetic field. That should be of a magnetic field. I have typos in here. Can't help myself. Okay, so let's recall what Ohm's law is really quick. Ohm's law is that the current is related to the applied electric field times some constant. Okay, we'll see what this constant is. If you know what this in basic electromagnetism in undergrad, what this is it's a conductivity constant. It tells us something about the conduction of electrons through a particular 2D sheet. Okay, it's going to tell us something intrinsic about the sheet. Okay, the two-dimensional sheet. So Ohm's law is the statement that the current of electrons in the 2D plane flows in response to an induced electric field, flows in response to an induced electric field, and that current is proportional to the electric field. My gosh, I have so many typos in this. I should have checked this before. I know I checked this. I checked these at least once. I don't know. This should be magnetic, right? Magnetic. And then where's the other? Electric. The proportionality constant is the conductivity of the 2D plane itself. Okay? That's this proportionality constant, and that's going to be the conductivity. Conductivity constant. Okay, let's see how we can get this when we introduce an electric field. Right, so let's begin. In order to recover Ohm's law, we can just add an additional term that incorporated the electric field. So we need to have the model look like this, okay? And it's not obvious why quite yet, but we'll see. Okay, this is the effect of the applied magnetic field. Theoretically, you might think, oh, okay, maybe this should be the thing we add for an applied electric field, but we also need to add this bit, okay? This bit here is different, and we'll see why we need to add this bit here. Notice how this is manifestly different from the Lorentz law that we already know and love. The Lorentz law is this guy right here. This is the force. Right? Force equals ma. Ma is the derivative of volume. But force here is, okay, we have the charge of our particle, which is, in the case of an electron, E. For a more generalized particle, we just say Q. But, okay, if we have E plus V cross B, right, so we have this E minus, well, we take the minus E out. This, okay, we would have E, or minus E, right, because we're taking minus out. So this thing here, this sign here is a little bit different, but the overall structure looks pretty much the same. But then we have this thing right here. This thing right here is going to be key, and so this is manifestly different from our Lorentz law. Okay, and this model. So this is the Lorentz model. This thing here is going to be called the Drude model, or I think I'm pronouncing that correctly. But this is the Drude model, okay? And the Drude model has this added bit here, okay? The Drude model is designed to describe the behavior of a charged particle in a sea of oppositely charged particles that they scatter off of, where the scattering time constant is tau, okay? So this is like a scattering effect. So when the electron is traveling through the external magnetic field, or when the electron is traveling in the plane, the idea here is that plane has oppositely charged particles in it, opposite to the charge of the particle that's traveling, and that particle is going to scatter off of off of all those other particles as it's traveling, okay? And the time it takes for the particle to scatter between each object is encapsulated in this time constant, okay? This constant is the average time between all the collisions, okay? So you can imagine if t was really big, the average time would be a really large amount of time okay? And if t was really big, then this thing goes to 0, okay? And then we just get a Lorentz model back. So in the limit, as tau gets really big, then we recover the Lorentz model, okay? So the Drude model, we have all this scattering to get from point A to point B. In the Lorentz model, we don't have a lot of scattering in this, okay, in the system. So if there's no acceleration in the particle in our system, then we could say this thing right here's the acceleration. Again, is the derivative of the velocity, the time derivative of the velocity. Therefore, we could say about the Drude model, this right here, right? Because that's just saying that this side is set to 0. All right. And so we can bring this to the side of the equation. We get this right here then. Okay. Then we can say, well, okay, let's divide both sides by m and multiply both sides by tau. And so we get this. Okay. So nothing too fancy yet. If there's no change in velocity over time, then we'll get a situation in which there's no change in the direction of the velocity vector, okay? So we call this situation Drude equilibrium, okay? So this is the Drude equilibrium. We can see that the Drude equilibrium will be written can actually be written as a matrix equation. It's weird to look at this and be like, well, this is a matrix equation. Well, let's see how this is a matrix equation. This is going to be the equation. We're sort of going to work backwards here. All right. So this matrix, let's see what happens here, right? So this matrix multiplied by our velocity, right, times the number of particles and the charge of those particles, is going to be equal to this right here, right? So we can confirm that this indeed is the Drude equilibrium in the following way. So we want to keep this in mind. Now we're going to work with this. Okay. And so this is just a constant. We bring this out front. The negative will make all the positive stuff in here go negative and the negative stuff in here go positive. So we have this times this is equal to this. Okay. It kind of looks like we sort of pulled this out of our butt, but it's not. It's not that. This is actually going to converge onto something quite interesting. So so we have this. All right. So what is it? So let's just look at this really quick before. So we're going to do the matrix multiplication now, right? So times this vector, and what we get is this. Okay. Then what we get. We can x prime and our y prime, we couple those together, bring the negative out. And then this guy here, this y prime, x prime, we have, if we bring out this constant, we have all this. This here, we have negative x, because we have this positive times a positive, or negative times a negative is a positive, which is this thing's positive. Negative times the positive makes that negative, right? So we have the negative of the sum, and then we have the difference between the two. Well, the difference between the two is actually the cross product, and we can actually see that when we cross product our original magnetic field vector, or perpendicular magnetic field vector, with the velocity vector. Okay. So here's that. If you remember what the cross product is, we do this and then we get this, right? We have the difference, right? This is just with the constant b, right? With the constant b, but here these are just constants. But we could see negative x, positive y, negative x, positive y. So this is actually the cross product between with the b vector, right? So this b, along with this, that's just a cross product between the two vectors. Right? So I'll highlight this just to make sure it's clear. This bit right here, that's just a cross product. Okay, and then we get this. And look, if you look at this is the equilibrium Drude model. Right, so the equilibrium Drude model is this guy. We really just manipulated this to get this. Okay? All right, what I'm going to do now is move on to the members only part of this. Right, so we were able to look at the Drude model. We were able to see how the Drude model is incorporated, or how the Drude model is made sense of in terms of a matrix. Okay. Next, we want to take a look at how this Drude model gives rise to not just conductivity, but a conductivity tensor. Okay. The end result of all of this is going to be, we're going to derive a Hall coefficient from all of this, right? So, okay, so if you're interested in supporting the channel, you can become a Patreon member and you can get more access to this. But let's go ahead and move on to the members only part of this.